Alright, I've got an example here about spherical coordinates, given a point P, -2, 6, 3, and vector A, which is y in the x direction, x plus z in the y direction, express P and A, the vector, in spherical coordinates, evaluate the vector at point P in the spherical system. Okay, so here we go. So let's work on transforming that point into spherical coordinates. So to do that, we need to remember that the coordinate rho, or excuse me, not rho. I've been working in cylindrical coordinates for a little bit. R is the square root of -2 squared plus 6 squared plus 3 squared. Okay, so we do that. We've got 4 and 36 is 40, 49, so that's actually 7. So that's nice. Okay, so that's the radius. Now, if we want theta, remember that's the inverse tangent of the square root of x squared plus y squared. So let me just write that down, and then divided by z, right? Z. Okay, so that's the inverse tangent of the square root of x squared plus y squared. So that would be square root of -2 squared plus 6 squared over 3. So that's the inverse tangent. So what do we have there? We've got square root of 40 divided by 3. So if we punch that in, we get up to 3 significant digits, 64.6 degrees. All right, and when you take inverse tangents, you want to be careful because we've got a positive number here, so the tangent is positive in the first quadrant, and the third quadrant. So we've got a ratio of 2 positive numbers, so that's quadrant 1, 64.6 degrees. All right, and then if we want that last coordinate phi, remember that's the inverse tangent of y over x, so we've got 6 over -2. So we punch that in, and we get 108 degrees. Again, we're going to be careful there. We've got a positive y coordinate and a negative x coordinate. So that's 108 degrees when we punch that in the calculator. All right, so we've got now our point P. So this is 7, 64.6 degrees, 108 degrees. There it is. All right, moving on now, we want to convert our vector into spherical coordinates. So for that, we need the transformation matrix. So we're going to take AR, we got AR, A theta, A phi is equal to, and again, you don't have to memorize these kinds of things here. This is good for your sheet of notes. Sine theta, cosine phi. It's the first guy there. Then sine theta, sine phi, cosine theta, right? And then we've got cosine theta, cosine phi, cosine theta, sine phi, and then negative sine theta, and finally negative sine phi, cosine phi, 0. So we'll just consult our notes or our textbook, make sure that we've written that down correctly. Now, times the x component of the vector field, well, there is the y times ax. Then the y component is x plus z, right? And there is no z component, so we've got 0 there. All right, so we carry that multiplication out, and things are going to get a little cramped here, but we've got AR when we carry that out. So row times the column, we have, let me just erase this. Excuse me. Okay, so row times the column. So we'll have y sine theta cosine phi, right, plus x plus z times sine theta sine phi, and then cosine times 0, so that's just 0. And then for a theta, the component in the theta direction, we've got y times cosine theta cosine phi plus x plus z times cosine theta sine phi, right, and then plus 0. And then for the phi component of our vector field, we've got minus sine phi, times y, so minus y sine phi plus x plus z times cosine of phi. Right, so that's what we've got. Now, we're still not there. We've still got some y's and some x's and some z's hanging around. So we need to recall that x in spherical coordinates is r sine theta cosine phi, right? Y is r sine theta sine phi, and z is just r cosine theta. Okay, so what we do is we plug this in for x, right? And we plug this in for y, and we plug this in for z. And then finally, and I'm going to write out the final answer just to be complete. We get our vector field A in spherical coordinates, and we can actually end up grouping some things together. For example, we will have we'll have 2r sine squared theta sine phi cosine phi, okay, plus r sine theta cosine theta sine phi, right? And that will be the AR direction, right? So that's what we get for AR there. Then plus, then we'll be able to group an 2r sine theta cosine theta sine phi cosine phi plus r cosine squared theta sine phi in the theta direction. Okay, and then finally in the phi direction we've got r sine theta cosine squared phi minus r sine theta sine squared phi plus r cosine theta cosine phi. Alright, so this is our answer. Okay, so finally, we're told that we need to evaluate what we just solved for at the point P. So our point P, this is r, right? And this is theta, and this is phi. So we can plug those in, right? And we can calculate things. But 64.6 is rounded already to 3 sig figs, and so is 108. So what we're going to do is we're going to calculate this exactly, and I'm going to erase some of my work here, and feel free to pause the video if you need to. Pause the video, but we're just going to keep some things there. Let's keep that. Okay. So I'm going to draw a right triangle, and we know, we'll start with the phi. We know that if we take the tangent over here, the tangent of phi is equal to 6 over negative 2. So what I'm going to do is I'm going to go over negative 2. I'm going to start here and go negative 2 in the x, right? This is y over x, right? And then I'm going to go up 6, not drawn to scale, and I'm going to call this angle phi. Not theta, phi. right? There's phi. So we see the tangent is opposite over adjacent, so opposite is 6, minus 2 is the adjacent, so this is the tangent of phi is 6 over minus 2. So what does that make the hypotenuse then? Well, the square root of 36 and 4, so the square root of 40, right? 4 root 10, 2 root 10, excuse me. So then we can say, well, what is the sine of phi from this right triangle? Well, the sine is the opposite over the hypotenuse, so that's 6 over root 40, right? So that's it exactly. We haven't rounded or anything. And we can get the cosine, right? The cosine of phi is adjacent over hypotenuse, so that would be minus 2 over root 40. So just from knowing that the tangent of phi is 6 over minus 2, we can get the sine of phi and the cosine of phi exactly. So then it's this that we plug in for the sine of phi. We don't just plug in phi is 108 degrees. We plug in the sine of phi is 6 over square root of 40, and the cosine of phi is minus 2 over the square root of 40. We plug in the cosine of phi is minus 2 over root 40. And similarly, we can do something for theta as well. So now if you're getting slick to this trick, because this is not the first time we've used this trick, let's see if we can pull off theta. So we know that the tangent of theta is the square root of 40 over 3. So that was this thing here, right? Theta is, if I take the tangent of both sides, I get the tangent of theta is the square root of 40 over 3. So think about it. Pause the video if you want. But what does that make the sine of theta? Think about it. Well, square root of 40 is the opposite now, right? Tangent of theta is opposite over adjacent. So the opposite is square root of 40. The adjacent is 3. So that makes the hypotenuse what? 7, right? The square root of 49. So the sine, which is the opposite over the hypotenuse, is square root of 40 over 7 in this case. And the cosine, then cosine of theta is just 3/7, right? 3 over 7. So that's nice. So we plug this, or we plug these things in. The sine of theta, right? We don't calculate the square root of 40 over 7 and then plug it in again. We just directly put in the square root of 40 over 7 into the sine of theta, and we directly plug in 3/7 in for the whole thing, cosine of theta, right? You don't want to just use 64.6 in there, because then that's carrying through the rounding. You don't want to do that. Anyway, so when you plug those in with r equals 7, right, the radius is 7, what you get is a equals negative 0.857 in the radial direction minus 0.407 in the theta direction minus 6.01 in the phi direction, up to 3 significant digits.